In order to succeed in space, we must be able to produce as much as possible on site, or in situ. But what are the most critical resources to harvest, and how do we do it? Today we are discussing I.S.R.U, or In-Situ Resource Utilization, which includes the collection, processing, storing, and use of materials found or manufactured on other astronomical bodies, such as the Moon, or Mars, or asteroids, or even the Sun itself. Today we'll be looking at 8 broad categories of I.S.R.U, providing shelter, extraction of volatiles, regolith processing, energy production, manufacturing and construction, agriculture, propellant production, and starlifting. And we'll go over them in that order because I feel it loosely represents your priority list, as for instance shelter and extraction of volatiles are what you need to avoid almost immediately dying from lack of protection from radiation and vacuum, and to get air and water to breathe and drink. And speaking of drinks, you might want to grab one and a snack to enjoy for today's episode. You will have brought those on your journey and presumably have some reserves, but they are your thinnest and shortest margin. You cannot live long without either. Alternatively, I've put starlifting at the end because while it is your ultimate I.S.R.U option, short of something probably impossible like raw matter and energy production right out of the quantum foam or vacuum, but also requires truly epic engineering and infrastructure to get going. Along with talking about the types of I.S.R.U and how to accomplish them, we also want to contemplate some of the philosophies involved. For instance, I.S.R.U can support both human and robotic space missions, but a lot of the I.S.R.U we'd like to do for humans is stuff that we'd like to have going before any human even sets foot there, or which were easy and foolproof options that could expand out from a ship on landing there in the same way a recreational vehicle can park and start expanding and unpacking sections or gear or hooking up to power or water. And a lot of that depends on how capable our robots and AI systems are. The more autonomous they become, the more I.S.R.U infrastructure they can establish in advance, digging shelters, processing volatiles, or even constructing or assembling living quarters, launch pads, solar arrays, or greenhouses. This isn't just a question of physical dexterity or rugged design, but also of decision-making, machines that can adapt to unanticipated terrain, identify usable resources, or improvise when a tool breaks. In the long run, intelligent automation could allow I.S.R.U operations to flourish even on hazardous or distant worlds, where it's impractical or too dangerous to send people first. At a key level, especially early on, I.S.R.U can significantly reduce the cost and increase the sustainability of space exploration by minimizing the amount of materials that need to be launched from Earth. But ultimately, our goal isn't just to make exploratory missions and science efforts cheaper, but to open the door to pioneers and businesses looking to build new lives and good prospects out among the stars, with bigger communities and civilizations to follow. This begins with providing shelter, and often is going to be needed for robotic missions too. As an example, the James Webb Telescope needs to be sheltered from sunlight and heat while performing its observations, and so it takes advantage of pre-existing shelter, Earth's L2 Lagrange point with the Sun, which is every bit I.S.R.U as taking advantage of a cradle to build your base in. L2 is a local resource that James Webb Telescope utilizes to get its job done better or cheaper, and it also has that big sun shield to further protect it from light and heat, which can be incredibly light since it's in deep space away from wind and gravity. Indeed, we often have to build sturdier than we need in space so that a device made here can survive being here and being launched from here, a problem something made in situ doesn't have. But how much better if a probe could land on a small asteroid, use it for shade, and extract the materials to build more extensive and robust sun shields? In space, we need shelter mostly from hot and cold, too much light or too dangerous of spectrums and radiation, which can be photons or charged particles. And we need protection from bigger clumps of particles, micrometeors, that might be hitting 10 times faster than a bullet, and even when tiny, might act as a powerful erosive force on equipment or domes. Now, as mentioned, this can include non-obvious shelter, like the James Webb Space Telescope and Earth's shadow, and could be for a robotic probe digging into a small crater for protection of instruments. But we usually mean people. Now, whatever ship they came in probably provides the initial shelter, and unless a simple lander or shuttle from a larger craft, probably was very complete in that capacity since people probably lived on it for many days, if not months or years first. But in most cases, ideally, you want to not land large spaceships on rocks or ice balls, and you want to have minimal shuttles or landers, preferably 2 for redundancy. So you want them to be able to unload everyone fast and with everything they need to get shelter for themselves going and to support that landing operation, like getting a landing pad ready, as regolith in places where there's no weather tends to be composed of sharp particles that damage everything they touch, and which get blown everywhere under the force of a landing rocket. We'll cover that more in our construction section, but for shelter we tend to assume a crater is a good first spot, as it is readily accessible, whereas a lava tube requires a bit more work to get at, and the crater covers you from more angles than a flat or elevated spot would. It also provides facilities built nearby a blast cover if a rocket explodes on the pad. Inflatable structures are one very good initial approach, as they let you get air and pressure and get out of suits for a bit, but they can puncture easily, and while a small hole is not going to be hard to patch and can be made quite robust, we tend to assume the intent is to use them temporarily or cover them over with additional rock or ice. In low-gravity areas, you could have very thick shells over top requiring very little support, and even someone using a shovel might not have much problem scooping out sufficient regolith to cover a fairly big habitat in a fairly short time. Though again, regolith particles are often unweathered and sharp and likely to slice your inflatable up. Using existing caves or lava tubes is also a good approach, but we can dig or melt into them too. This is early operations. We are not thinking of grand homes or factories or operational bases yet, or glass domes for growing food, or rotating segments to provide gravity by spin or enhance what's already there. Just basic shelter, something you could survive in for several days or in a pinch to make work for months. You do not necessarily want anything permanent yet either, as you may need to move. You might be a roving explorer, living in something akin to a tracked vehicle, or you might only want to be in a spot for a few days to get a landing pad or access to ice set up before shifting base a bit further away to a better spot for residence, which is never too close to your landing pad. That's not exactly a safe operation. Again, why crater rim walls are a nice natural barrier for containing blasts or protecting from them. This initial base might include landing, popping a tent open to inflate, then shoving regolith on it, or it could be a planet with some air and gravity where your ship lands on an ice pad and then sucks up the water it just melted with its rockets to spray over an inflatable or skeletal frame to make an igloo with. It could also be that you drop a probe with a nuclear power source to melt or dig caves for you and take the other material to build landing pads. You might dig into a crater rim wall and use the material you dug out as a building material for shelter on the rim just outside that crater. You can build a much larger hollow structure from the material you dig out to make a cave than the size of that dug out cave, even with thick walls on that structure. Thick walls protect from radiation, micrometeors, and air and heat loss. Or gain, too. You could survive on an airless world like Mercury, blasted by the sun, by finding a crater and extending a reflective umbrella shade over it, one who supports our poor conductors of heat, and then hanging yourself or your tent down from that shade or up on stilts from the floor, like a simple version of our mushroom habitat. And in deep space, far from warmth, such a reflective shade might be inverted into a parabolic dish to focus more sunlight into some ice cavern you dug out, or indeed to help you dig it out by melting ice at the focal point, or sublimating it into vapor on airless worlds. A compaction machine able to ram regolith into bricks or sturdy flat surfaces, or ways to make something like concrete out of local materials, is also invaluable. In-Situ is not about making everything you need on site, though that's ideal, and the other half of it is the compact and easy toolbox for survival and getting going. Some 10 square meters inflatable quilt with a reflective side and an absorptive side might only need to weigh 100 grams or a quarter of a pound and be inflatable off your expended breathing gas, carbon dioxide, or simply oxygen rich with it that you can't easily scrub or recycle. It might fold up into some small pouch that's ubiquitous on spacesuits. It's also a good reminder that In-Situ is not just about bringing the right tools or making use of the resources at that site, but also reusing and repurposing your existing gears and supplies,
and recycling the expended ones. You need more air to breathe and water to drink, but your exhaled and expelled gases and liquid still has value, so you also want some way to store them too, as you need shelters for your spare air, water, and waste.
All the better if those reserves can be kept smaller because you are very good at recycling, and of course at I.S.R.U. in general to get new ones if your reserves get compromised. But recycling isn't just a bonus, it's a vital form of in-situ resource utilization. Nearly everything a human crew discards, from food scraps to packaging to CO2 exhaled into the air, has the potential to be reclaimed. Compact, modular recycling units might extract water from sweat and waste, recover rare metals from electronics, or break down plastics into reusable polymers. Even waste heat from machinery can be recaptured for climate control or water processing. In the closed-loop ecosystem of space habitats, trash is not garbage, it's a raw material waiting to be reused, or a new resource, like the methane given off by various waste.
Speaking of that, extraction of volatiles generally means getting air, water, and fuel, and tends to focus mostly on water, ammonia, and methane, which are generally superabundant everywhere that's not too close to the sun. They are made of hydrogen, the most abundant substance in the universe, plus either oxygen, nitrogen, or carbon, which are also very abundant. It is not limited to those and can include hydrogen gas, nitrogen gas, carbon dioxide, or even something like hydrogen sulfide, which might be blasting out of a volcano on some place like Jupiter's moon Io. Volatiles derives from the Latin word volatilis, which means to fly, and in scientific context, it describes materials that can easily evaporate or sublimate, turning from a liquid or solid into a gas at relatively low temperatures. The volatility of a substance is a critical factor in planetary science, astrophysics, and the search for life, as it influences the composition of planetary atmospheres, the presence of liquids on planetary surfaces, and the potential for habitable environments. In I.S.R.U., identifying and utilizing volatiles is essential for supporting human life and operations on other planets or moons, or asteroids or spaceships and space habitats for that matter. Knowing what you can cannibalize from your ship's stores to replace a vital loss is also a type of I.S.R.U. Water is a critical one because besides being what you and I are mostly made of, along with everything we eat and drink, it is also very easy to turn into breathable oxygen and fuel for rockets or vehicles, or fuel cells for that matter. This is your most critical Phase 2 operation because the largest chunk of mass of your default spaceship is going to be fuel, air, and water, often considerably more than the mass of the ship itself or its payload, so getting those volatiles is your first and biggest mass and cost savings for missions, beyond the raw bulk material for protective shelter and landing pad. On most objects in this universe, frozen ice of water, methane, and ammonia will be readily available and volatiles can be easily extracted from them. In deep space, they often float around freely, so you could hypothetically resupply by capturing tiny amounts in the not-quite vacuum if needed, far from any rock or ice ball. However, ices of any type are rather uncommon on most bodies closer to the Sun. Earth and Mars have them, the Moon might have some. Venus doesn't have ices but has tons of those gases, so you don't even need to melt them. See our episodes on atmospheric mining for more discussion of that approach. Also, some asteroids and maybe even some dark craters on Mercury might have ices, but mostly all those rocks near us don't have ices, or precious little of them. Which means if you want volatiles there, you need to process them out of the rock or regolith. Most rock is made largely of oxygen, and on the Moon, for instance, the bulk and approximate composition of lunar regolith, starting from smallest to biggest on the periodic table, is 10 parts per million lithium, 2 to 5,000 parts per million sodium, 1,000 parts per million potassium, 70 ppm fluorine, 50 chlorine, 800 phosphorus, 130 vanadium, 200 parts per million nickel, and 8 parts per million copper, among other things. For raw weight percentages of more common substances, magnesium is 5.5%, 10% for calcium, 20% for iron, 10% aluminum, 20% silicon, 1% titanium. And most of the rest is oxygen, and concentration varies by location a lot. This is where you're getting all your building materials, simple or complex. And extraction is likely to be either by replicating conditions and facilities on Earth, or using processes better tailored to vacuum or low gravity, Outside a place like Venus or Jupiter, getting access to regolith to process is going to be the easy part. You may have noticed I didn't mention anything about hydrogen or helium or carbon or nitrogen, and again, while those are hyperabundant in deep space, they tend to get blown away from low-gravity bodies that also get a lot of sunlight and solar wind. Solar wind, incidentally, is mostly hydrogen followed by helium coming off of the sun, and at speeds any rocket we've ever made would envy. As we discussed recently in Settling Mars, Phobos, and Deimos, it is possible to make fuel out of oxygen and just about any material oxygen bonds to, but electrolysis of water to make hydrogen and oxygen is much easier and lower energy than most other options. If you've got enough energy, you can make this work as a supply of oxygen and fuel, but while producing vast amounts of metals probably lets you sell them for all the water and nitrogen you need, you will need to get good at recycling them at many places. Alternatively, oxygen is likely to be the main waste product of most regolith refining and smelting processes. If you've got enough power, you can make almost any place in space work, but that takes us to energy production, because without it, no place will work. In the inner system, sunlight is your big power source, feeding your plants, powering your solar panels, lighting and warming your buildings, and even running solar kilns to smelt metals. There's no rain or wind to block or damage panels, though unfiltered sunlight or particles of regolith can be rough on them. In many cases, especially further from the sun where things get dimmer, you will use large amounts of cheap reflective materials, like metals you extracted and polished locally, to focus sunlight onto a panel or solar thermal receiver, and you can protect that from dust easier and also make panels that aren't reflective to the more brutal wavelengths of sunlight. But energy production is not limited to sunlight, nor is it necessarily best. Fissile materials will often work great, either by fission or radioisotope decay, and fusion is awesome if we can make it work, as are micro black hole power generators and vacuum or zero-point energy if you've got it. See the episodes The Nuclear Option, Fusion Power, Kugelblitz black holes, and vacuum energy for more discussion of those options. Another advantage of space is that it's relatively easy to move power around it or store it, as wires are easily made and work well in vacuums, and existing superconductors can function at local room temperatures on most places significantly colder than Earth. You can also beam energy around as concentrated sunlight or convert it into microwaves and store heat for turning into electricity in the equivalent of a big thermos, since those work by preventing heat loss by conduction or convection, just allowing radiation, and that's all that can happen in a vacuum. You can use nuclear power for dark places or periods or store heat from sunlight. By default, your best power supply for most early operations though is an RTG, radioisotope thermal generator, as while they are not cheap or efficient, they are incredibly simple, durable, and reliable, and mass production of those by nuclear breeder reactors may be a major economic sector simply for their portability and reliability. And while RTGs are not efficient, their waste is in the form of heat. So often, when you'll need energy in cold places for that anyway, they are entirely efficient. Beyond staying warm, or alive, or lighting food crops, what you mostly want power for is manufacturing and construction, as that lets you expand not only your base or settlement, but also expand what you can make there, so you don't need to import or buy it, and indeed have something to export. Probably the most popular option for discussion is 3D printing, typically using local materials to 3D print structures, tools, and components. This can include building habitats out of regolith to protect against radiation and micrometeorites, or it could be a range of objects so wide and intricate as to parallel a Star Trek replicator, though there are some real limits on what 3D printers or self-replicating nanobots can do, or do well, as we discussed in our Santa Claus Machine episode. A lot of times a bigger supply chain running bigger devices, like smelting kilns, is going to be faster and more efficient at production. But again, a lot of in-situ production is about saving mass, especially in the early days. We do not necessarily want to have everything made at places either, as it limits the need for trade, which tends to be a unifying factor for humanity. You can bring along or reuse a lot of small and intricate devices, your microchips and so on, but the ability to 3D print a basic screwdriver or some tool or widget that was too bulky or non-urgent to bother bringing along, or maybe bringing along a spare, is exactly what a 3D printer can do well. Even if the printed tool is weaker or inferior to one coming out from a high-tech and specialized production facility somewhere. It is nice if you can select from an inventory of a million tools or basic devices like a panel of reflective or transparent dome material and dump in some simple feedstock and get those items out. In many cases though, you will want a specialized production of something to make it more efficient, and for instance in asteroid mining facilities, it might be there's a dozen major manufactured products you need in bulk to work out there, and most mines pick one or two of those to specialize in as a sideline to mining, and trade them to neighbors for the other items, or food for that matter. Given that food is something we all like to have every day, and preferably a few times a day, you might wonder why agriculture wasn't higher on the list, but that's because it isn't very quick to happen. You can melt an ice cube down to drinkable water very quickly compared to turning that water into edible food from a plant. You generally are going to need months to go from barren rock to even the simplest hydroponic crops actually growing and yielding food. So you might think you need to start it right away, but you probably focus on bringing food to begin with, and you also might have had some fresh vegetables or fruits already growing on your ship. Indeed, your earliest crop might well be big algae vats for processing regolith into something more soil-like. And for producing algae to use a feedstock for plastics, or livestock for that matter, or eating yourself, though I suspect unless we get real good at printing synthetic food from such feedstocks, people will prefer to eat pre-packaged stuff until full-scale agriculture comes online. Folks can talk about necessity and eating algae or bugs for protein, but the reality is that space is a voluntary affair. As important as space might be for humanity's long-term future, and handy it might be for communications, power production, or certain materials only producible in microgravity, humanity does not actually need space. All the problems we have currently with humanity and our own one lone planet either convert wholesale to space because they are caused by people and thus will come with us wherever we go if we don't solve them here, such as requiring us to master certain recycling or ecological techniques. So we don't need another planet, let alone any dead rocks. We just want them to help us grow greater as a species, and thus you have some real limitations on what you can expect folks to put up with once the novelty of space wears off. See our Space Farming and Agricultural Awards episode for more discussion of details on producing food, or what farming-focused space communities might be like. But the key is that you probably have some limited hydroponics on every ship and station to help with air recycling, free carbon dioxide scrubbing, stress, psychological issues, and of course to get some fresh produce and tasty herbs into the diet. Beyond that though, it isn't likely to be a high priority to scale up, especially as food production is one of the hardest things to automate thus far, and most space-based new facilities have some mission people on it are tasked with that massive food production is going to distract from. Food calories are also not very space or mass consumptive as fuels go, micronutrients and vitamins even less so. Once we exclude fruits, green leafies, and some other veggies, which are mostly air and water, a 1-year supply for someone might not take up much more room or mass than a spacesuit, and the waste products, if stored, are completely reusable for future production. So early production is mostly about fresh food, air recycling, maybe water recycling too, and the psychological benefits of having something green and alive nearby. And I suspect much like modern society, everyone else imports their food from specialist farming habitats, especially everything that stores well. Highly automated gardens will likely be a thing, and whatever automates most easily while being pleasing to humans to have around is likely to be what we see. Propellant production might also seem like a strange thing to have late on the list, but you don't technically need propellant until you want to leave your new base or settlement. It is vitally important though. Space is huge, so getting the fuel and propellant to move around it is a big deal, but fuel and propellant are not always synonymous. The Sabatier reaction and electrolysis is our big go-to for fuel, especially on Mars where there's plentiful water ice and carbon dioxide. You can make fuel out of either splitting that water into hydrogen and oxygen for burning, or with the carbon dioxide, make methane and oxygen for burning, which is easier to store too. And as mentioned, with enough power we can generally make a rocket fuel out of oxygen and just about any material that bonds with oxygen. In these cases, the fuel and oxidizer is also our propellant as we burn them and fire them out the back of the ship to propel it along. But in reality, chemical rockets have a real limitation on maximum speed, and one barely good enough for slow interplanetary travel, because your speed for your ship is based on how fast your propellant can leave it, and their speed is based on how hot they are made in the combustion process. which is limited by both basic chemistry and the temperature at which your rocket components start melting. This is what we like about ion drives, as they are simply some ionized particles, ones with a charge being propelled by electric or magnetic fields out the back of the ship. And they can be moving very fast indeed, and while some materials are better than others, depending on the drive type, just about anything can be made to work and to outperform the best chemical fuels. Assuming they aren't your power source, of course. We detailed many ion drives and other advanced drive types in our Advanced Spaceship Drive Compendium episode, including interstellar options. Indeed, even something like a gravitational assist on a spacecraft is an example of the principles of I.S.R.U., as would be slowing down at a new star by dragging on the local interstellar medium magnetically rather than burning fuel. You use what is available locally to your advantage, and it's always been one of humanity's great strengths. Our adaptability to survive in harsh climates is all about I.S.R.U. But when it comes to propellants and ion drives, here your fuel is whatever you're using to run those electric or magnetic fields to produce electricity with, so there may be vastly more energy-dense options like nuclear or simple solar panels on the ship borrowing from the sun. And indeed, the solar wind off the sun is mostly ionized particles, so various solar sails can use those photons of sunlight or the ionized particles as free fuel or propellant, another example of in-situ resource utilization. Speaking of using particles from the sun, Starlifting is the final and ultimate section of I.S.R.U., and one you can get more details on in our episode on Starlifting, but the basic approach is to harvest your own sun and let it pay the bill. Jupiter has more mass on it than every planet, moon, and asteroid in the solar system combined, and yet the sun is still 1,000 times more massive than it, and there's no element in the solar system that isn't more abundant in the sun than everywhere else combined. Everything in the sun churns around, so heavier elements are near the top, not just the core. And by using the same principle as an ion drive, we can electrically or magnetically suck or blow material off the sun. Again, this is how solar wind works to begin with. And we can use reflective mirrors to bounce light back down on a patch of the sun so that heavier elements are moving faster and easier to blow off. You capture them magnetically and sort them the same way. A heavier ion's path bends less in a magnetic field than a lighter one, similar to a rainbow. And you can dump the excess hydrogen back down on the sun if you want. Indeed, this is a great way to extend the lifetime of any star, as they typically die long before running out of fuel by being poisoned by buildups of helium and heavier elements, though some stars are less convective than others and would be harder to alter the core concentrations of. Some stars also have a lot less metals in their sun or hanging out in planets and asteroids, so often starlifting might be critical to any attempts to build up a new star system, and you would generally have more than enough materials to build the apparatus there. They'd be worth importing even across the interstellar void if not. Here on SFIA, we are no strangers to big ideas, like mining stars for fuel or building Leviathan starships the size of small continents to haul us boldly into the void, but even the biggest dreams had to contend with the very real problem of space trying to kill you, constantly. So what is the unlikely hero of deep space travel? Maybe it's not force fields or fancy alloys, but plain old water. In Fishbowl Starships, this month's exclusive, we explore how future vessels might be wrapped in water, not for swimming laps, but for surviving the harshest environments in the universe. Water pulls triple duty as radiation shielding, micrometeoroid armor, and thermal regulator, all while keeping your crew hydrated and your hydroponics alive. We'll see what other use it has and how it stacks up to other materials. You can watch Fishbowl Starships now on Nebula, where all my episodes go up early, ad-free, and often with bonus content you won't see on YouTube, like our monthly exclusive and extended editions. And if you enjoy material science, you also find other brilliant creators there like Real Science, whose episode on why spider silk is stronger than steel explain why it might just work for a megastructure's tensile supports. Want to bring friends? Nebula's got guest passes. Share a full week of content with no card required. Want to skip monthly fees forever? Nab a lifetime membership for just $300 and unlock everything forever. Or go with the annual plan for only $36, cheaper than a radiation suit and far better at surviving cosmic rays. Join us today at go.nebula.tv/IsaacArthur, and let's keep building the future, one outrageous idea at a time.
Incidentally, you may have noticed the audio shift a few times during this episode. That's because this episode originally came out on Nebula as one of those monthly exclusives, and I bring most of those over to YouTube after a year or two, but often tweak the episodes or add extended bits I feel need more discussion. And my speech impediment has improved since then from a lot of speech therapy and surgery. As an example, earlier this month we were looking at interstellar travel and how to survive those very long journeys, and it made me want to add a bit more on this episode about not just acquiring resources, but recycling the ones you had as being a very important aspect of I.S.R.U, especially on interstellar ships. Travel to other star systems is a good place to close out on too, as this requires mastery of I.S.R.U principles, while hopefully we would have excellent automation able to serve as vanguard of new star systems to help set up facilities and supplies in advance of human explorers and settlers. Any colony mission must be nearly entirely independent of trade and help from Earth from the moment they leave the docks up in orbit. As we reach out to other worlds in the solar system, we can experiment and learn what works best, and how things we learn on Earth will make us better at space-based I.S.R.U, and vice versa. Like I said, we don't need space to survive, but it is our path to greatness, and we do need those lessons of I.S.R.U we will learn in space, not only to survive there, but to better thrive down here.